flow of fluid through a channel is an important process in the earth sciences as well as in other science, engineering, and medical fields. In this group of 3 videos, I will first introduce some examples from the earth sciences where channel flow is quite important. I'll then do a physical and mathematical analysis of the channel flow problem. And finally, I will discuss how channel flow leads to a certain amount of discharge of a fluid from the channel and how we be in position to calculate what that discharge should be. So some examples from the earth sciences. Probably one of the most common examples is flow of fluid down a stream, shown here in a kind of slowly meandering stream. And we can look at a cross-section through that stream and calculate how much water is flowing through the stream. But what we'd like to know is what is the velocity of the fluid at any point in the stream? And we'll talk in detail about how we might get at that problem. There are other examples that are very similar to the stream flow. We could apply it to magmas flowing from a volcano. It flows in a channel much like water flows in a stream. And I'm not going to deal with this problem in detail today. Chris Paola will come back and talk about it in more detail. But we might call this a gravity-driven flow, where it's the fact that water being uphill would like to move downhill, driven by gravity. A second example would be flow between 2 parallel plates. And an example that I've shown here is flow, for example, at the Shiprock exposure, volcanic exposure in New Mexico, where rock fractured and magma came up between the fracture. And you could think about that as a fluid moving through 2 parallel plates, driven in this time rather than by gravity, it's actually driven by a pressure gradient. There's high pressure at the base, basically explosively moving the magma up between the rock. And I've shown on the inset on the upper right-hand side an example where you can see a solidified section which shows a diabase dike cutting through a granitic rock. And this is the case where what's driving the flow, again, is a pressure gradient. There's higher pressure at the bottom, lower pressure at the top. Another example might be a flow between 2 parallel plates, but in this case, we might think of the bottom plate as being stationary and the top plate moving, as shown in the sketch in the upper left. And it might apply, for example, to motion in the asthenosphere in Earth's mantle, with the lithospheric plate moving over the lithosphere and dragging or pulling the fluid along with it. And we'll do that, an example of this, and we'll look at it in a little bit more detail in just a few minutes. Another possibility is rather than flowing between plates, we might flow through a pipe. This would be a common one shown in the upper right of water being driven out of a pipe. It could be your garden hose, where there's high pressure water at the house and lower pressure out in the garden, and the water flows in that pressure gradient. Another example of pipe flow would be flow in a plume nucleating, say at the base of the upper mantle or base of the transition zone, or maybe at the base, at the core mantle boundary, and the fluid moving up vertically up through a tube shape or pipe shape region. And we're going to talk about later on taking this to a micro scale and look at flow or permeability of a rock sample to a fluid. In this case, shown in the upper left, there's water flowing through a rock. And if we zoomed in and looked at the sketch in the lower right-hand part of this figure, or lower left-hand part of the figure, we see a sketch of some grains, and then the flow by the blue arrows. You can see how the water is flowing through the channels between the grains of the rock. And so this is a pipe flow problem, but at kind of a micro scale. What might be happening inside of a rock. And we'll take the analysis that we build up for more macro scale flows and talk about them in terms of a micro scale and calculate a property called the permeability. How easy is it for a fluid to move through a rock? And in the figure in the lower right is sort of a skeletonization, might have been done, probably was done using X-ray tomography. And there was a fluid put in the channels through the rock. The fluid was more dense than the rock. And so when you did X-ray scattering from this rock fluid system, the fluid shows up and is captured, and basically you can digitally remove the grains, and you can see the fluid channels, and you might want to model how fluid could flow through that complex structure. And it basically is a pipe flow problem, taking from the macro scale down to the micro scale. Okay, so we want to set up the pipe flow problem, or the channel flow problem, and talk about physically what's happening, and then talking about how can we set up some equations to describe this physical situation. And so I've shown in this figure basically two driving forces for making the fluid move. There's a plate being pulled across the top from left to right at some velocity that I've called V1 0. And at the same time, there's a pressure gradient where there's a high pressure on the left-hand side, a lower pressure on the right-hand side, and the high pressure is pushing the fluid toward the low pressure side. So there's a pressure gradient. And I've described that in the center here as a derivative of the pressure with respect to position. And that is a negative quantity because there's high pressure on the right, low pressure on the, high pressure on the left, low pressure on the right. But the coordinate system, the x-axis, the x1 axis, is running from left to right. And so it's changing in a positive sense while the pressure is decreasing. And so that ratio of change in pressure to change in distance is a negative number. So in the upper right-hand corner, I've drawn the coordinate system for you, and we're going to use this coordinate system throughout the discussion in the set of 3 videos. And the x1 axis is going to be pointing to the right. The x2 axis points downward, like going from the top of the surface of the Earth downward into the Earth. And the x3 axis is shown by this x, so it points into the screen. So that's the coordinate system we'll use. And we're going to talk about the velocity as a function of vertical position, and that is a function of x2 in the system. And what we can see right away is that the bottom is fixed. That's what's indicated by the series of slash lines at the bottom. And the channel extends from x2 equals 0 at the top to x equal h at the bottom. So that's the height or the depth of the stream or the depth of the channel that we're talking about. And the velocity at the bottom is 0. Right? The fluid, we'll say there's a no-slip boundary condition. So the fluid is stuck to the bottom, stable bottom, non-moving bottom of this channel, whereas the top can move. So there's a velocity gradient. The velocity is high at the top, and it's low at the bottom, and it's somewhere in between as you go through the channel. And it's that behavior that we want to talk about today. We want to find an expression that describes the velocity as a function of this variable x2. We want to know the velocity of the fluid flowing in the one direction, but as a function of position, vertical position in the channel. So that's kind of the prescription of what we want to do. This is the setup that shows the conditions that we're going to work with. Okay, so here's what we're going to try to do. We want to find an expression for the velocity as a function of vertical position. And we also want to know what the shear stress is as a function of vertical position. So x2, again, is the vertical position, the up-down position. And we want to know how the velocity and the shear stress change as a function of position. So we want to know two quantities, velocity v, and the shear stress tau. And so it means we have two equations, and so we're going to have to solve for those two equations, and we want to know what the appropriate boundary conditions are. So let's see how we can tackle this problem. So here's the problem. So already we know something from discussions in class. We have an expression for the shear stress as a function of vertical position, and it's related to the gradient and velocity, right? So we want two quantities. We want the velocity and we want the shear stress, and we have one relationship already between them. The second relationship we can get by doing a force balance on some element of fluid inside this system. So here's the little element we're going to talk about, this little gray box. And you can think about it extending back in the x3 direction. It has dimensions in x1 and x2 in the plane of the view. And what we want to do is to look at the force balance on that object and use that as a way of getting a second equation. So here we go. Here's that same little gray square. I've shown it in 3 dimensions. And it has forces on it from two different processes, or 2 different phenomena. First, we said there's a pressure gradient, right? So there's a pressure on the left-hand side and a lower pressure on the right-hand side. But there's also a shear stress on this cube because this plate on top, if we pull that plate across the top of the fluid, it's going to exert a shear stress on that upper surface. And so I've shown the shear stress here on the top, and here's the shear stress on the bottom surface. Again, our coordinate system is it runs from x2 as the vertical dimension. And so at the top, the coordinate of the top surface is x2. And the coordinate of the bottom surface is down some distance, delta x2. And so the coordinate at the bottom is x2 plus delta x2. All right. So we have 2 forces. We have a shear force on the top surface, and we have a pressure force on the vertical horizontal surfaces, vertical surfaces on the sides. Okay, and now we need to do a force balance. And this is, we're going to assume that the system is in steady state. That is, that it's moving at a constant velocity. There's no acceleration. And so we can do a force balance. And if we sum up all the forces, they must sum to 0. The plate is moving, or the fluid is moving, but it's moving at a constant velocity. And therefore, the forces have to sum to 0. And so the task we have is to find force 1, or force on the top, force on the bottom, force on the left, and force on the right. Sum them up and set it equal to 0. Okay, so we need to do a bit of math to get there. And to do that, I'm going to switch over to this side screen. So the task now is to do a force balance on this cube of material that we extracted from our stream, or from our fluid as it flows. And we need to, first we're going to calculate the force on the top surface and on the bottom surface of this block of material. That is, we're going to calculate the force due to the shear stress. And to do that, the first thing we need to do is I need to remind you about Taylor expansions. So we're going to do a Taylor expansion. We're going to do a series, a Taylor series. And to remind you that if I want to expand a function f, which is a function of some spatial variable x, that I can, and I want to expand it about the point x is equal to a, then I write this as the function f evaluated at a, the point about which we're doing the expansion, plus f prime, the first derivative of f with respect to x, evaluated at a, times x minus a, all that over 1 factorial, plus f double prime, the second derivative of f with respect to x, evaluated at a, times x minus a squared over 2 factorial, and then plus higher order terms. And if we make x minus a small enough, we can ignore higher order terms. We can ignore the second order term even, and we'll keep only the 0th order term and the first order term. And we'll ignore the higher order terms because if x minus a is small, then x minus a squared must be extremely small. And just to remind you that what we mean by f prime of a function x is just it's the derivative of f with respect to x. And if we want to know f prime at a, it's just equal to the derivative of f with respect to x evaluated at x equal to a. Okay, so with that, we can now apply it to the stress and calculate how the stress changes as a function of vertical position. Okay, so let's take the stress. We're going to expand about the point x2 plus delta x. And we can write this in terms of a Taylor expansion of tau, the shear stress on the bottom surface, is equal to tau of x2 plus delta x2. And that's just equal to tau at x2. So we're going to expand about, that's our a value, x2. So we're trying to calculate the stress. Knowing the stress at A, or at x2, we want to find the stress on the bottom surface. So it's equal to the stress on the top surface plus the derivative of the stress with respect to x2 times the quantity x2 plus delta x2 minus x2 divided by 1 factorial, which is 1, and then plus higher order terms, which we're going to drop. Okay, and so I can write that tau of x2 plus delta x2 is equal to, approximately, I should say, because I've dropped higher order terms, it's tau at the top surface. So tau, the stress at the bottom surface is the stress of the top surface plus the derivative of tau with respect to x2 times delta x2. Okay, so that's what the stress at the bottom surface looks like. All right, and if we want to convert stresses to forces, because we're not going to do a stress balance, we're going to do a force balance. And so if we want to calculate the stress or the force balance, just balancing the force on the top and on the bottom, then the force on the top surface, the force is in the negative x2 direction, so that's tau at x2 times the area, and the area that it's operating on, when we go back and look at the figure, you'll see is delta x2 times delta x3. And then we have to add to that, balance that with the force on the top surface, and that's equal to tau on x2, right, plus d tau dx2, which is just what we derived, times delta x2. Okay, so those are the forces on the top and bottom surfaces. And now we have to, oops, I need to multiply that by delta x2 times delta x3. And now the forces on the left and right surfaces, the force on the left surface is pushing to the right, so we'll make it a plus. So it's P, which is the high pressure side, times, and it's operating on an area delta x2, delta x3. And I hope you caught my mistake. This up here should be delta x1, and this one should be a delta x1. And then the force on the right-hand side pushing back toward the left is the low pressure times delta x2, delta x3. And we sum up all those forces, and that has to be equal to 0. Okay, so it's a force balance, balancing the pressure forces with those induced by the shear stress. And if I cancel out all the delta x3s right away, and I see I have a delta x2 here, that will cancel with that delta, or that, I'm sorry, I have a tau evaluated x2, which will cancel this one. So we've summed the forces, set them equal to 0, and now we're going to simplify this expression. And if we do, we're going to end up with d tau dx2 times delta x2, delta x1, plus pressure on the high side minus pressure on the low side times delta x2. We can cancel out the delta x2s, and we're left with an expression. And if we take the limit as delta x1 goes to 0, we can convert this to a differential equation that looks like the derivative of the shear stress with respect to x2 minus the derivative of the pressure with respect to x1 is equal to 0. Okay, so that's going to be our first equation. We'll call that number 1. Our second equation we've already seen. It appeared in the earlier slide, and it's something that we've talked about in class, and that was a statement that for fluids, a Newtonian fluid in particular, the shear stress can be written as the viscosity, which is characterized by we use the Greek symbol mu for viscosity, times the gradient in the velocity with respect to vertical position, x2. So that's our second equation. Okay, so now all we have to do is solve those two equations, and we can calculate both the how the shear stress changes as a function of x2, and how the velocity changes as a function of x2. So let's move back to the overheads, and I've just written the two equations that we derived so you can see them clearly. You won't be confused by my handwriting. And we have an expression now for the gradient in pressure related to the gradient in shear stress, and we have an expression for the shear stress written in terms of the gradient in velocity. And the next task that we'll handle when we go to the next or the next part 2 of this series is we'll solve this and we'll come up with explicit expressions for both shear stress as a function of position and velocity as a function of vertical position through our flow.